This week, our project is going to be solving equations, and we're going to solve a particular kind of equation, but not the traditional particular kinds of equations that you solve in your algebra class. I want to think about solving equations by reading the expression like we've done before, figuring out what operations we're performing and what order we're performing those operations. And then I want to solve the equation by performing inverse operations in reverse order. So this is not, for those of you who have been through an algebra class, this is not really something new. We're just talking about it a little bit differently. This is going to be a variation on the do the same thing to both sides of the equation. So this is a variation. For those of you who are familiar with that phrase, this is a variation on do the same thing to both sides. This is a variation on do the same thing to both sides. This is a variation on maintain balance in the equation. So it's a variation on that, do the same thing to both sides of the equation. So the form that we're going to have the equations is that we're going to have the equation that we want to solve is going to look like an expression equals some constant. So the form of the equation is going to be some expression or some function equals some constant. In particular, we're going to start off with an expression or a function that only has one instance of the variable. So we can read it as a bunch of things happening to the variable. Then everything else will be kind of branch off of that. We'll come up with different strategies if the variable appears more than once. We'll have to learn how to do that separately. But this is an expression or a function in which the variable appears one time. So the restriction is that when we're going to do inverse operations in reverse order, we have to have only one instance of the variable so we can read exactly what's happening to the variable. The goal of to solve the equation is to figure out what variable we put into the expression so that the output is the constant. So the game is going to be to figure out what happened to the x, what x will get, sentences are hard today. The game is going to be what value of x can we put in the expression and come up with the constant on the other side. So the game is to find the input for the expression that will produce the desired output. And that output is going to be the constant. So the input is going to be the variable, and the output is going to be the constant. This is not a game that we're unfamiliar with. So when we look at an expression, we look at an equation, we'll have some kind of expression, 2x, and we're going to set it equal to some constant, 10. And the game is to figure out what value of the input, the variable, will give us the output, which is the constant on the other side. Here's the expression, here's the constant, and what value of x will give us 10. What does x have to be so that when we run it through this expression, will give us 10. So start off with things that we're familiar with. This says 2 times something is equal to 10. And the question is, what value of x do we plug into 2x so that we get 10? what value of x do we plug into this expression to get a result of 10? Let's say this result. That's the equation game that we're playing. We're familiar with a lot of these equations already. We found out at the beginning of the class that a lot of you have been through an algebra class already. We're just learning to reframe the things that we already know so that we can expand them to more complicated scenarios. So in this equation, nice and simple, it says that 2x is equal to 10. And a lot of us know that we should divide both sides by 2 and come up with x equals 5. Some of us might just be looking at the equation as a question. 2 times what is 10, and answering the question 5. So what we want to do is focus on what's going on when we think about this so that we can apply it to more complicated scenarios. Because a lot of times if we do things that are automatic very often, we don't really, it's hard to expand on, to generalize the process because we've internalized the process so much, we don't even think about what's going on. So we know that the answer is 5. What we're going to do is I want us to read the expression. I want us to write down what's going on in the expression. That is to say, I want to write down what does the expression do to x to turn it into 10? How does the expression turn x into 10? How does the expression turn x into 10? That's what I want to read. That's how I want to read the equation. I want to say the equation says 2x is equal to 10. I want to think of the expression or the function as doing something to x and turning the x into a 10. So if we want to read the operations that are going on. So if we start off with the x, the first thing that happens is that the only thing is that we multiply by 2, and then we end up with a 10. That's how this expression turns an x into a 10. The one thing that it does is that it multiplies by 2. So to turn a 10 back into an x, we're going to perform inverse operations in reverse order. So I'm going to have my weird shorthand. This is the weird shorthand we developed for reading expressions. And now we're going to use it to read expressions backwards. To turn 10 back into x, we're going to do the inverse operation in reverse order. We're going to divide by 2. That tells us what to do. Take the 10 divided by 2. 10 divided by 2 is 5. Start with something that we can verify is correct so that when things get more complicated, we'll know that our process will work. Just testing out the process. All right. Let's include some more operations. Once again, we want to think about how does the expression turn the x into a 10? That's what we're trying to figure out. So let's suppose we have a different equation that says, say, 2x minus 8 is equal to 10. So now, once again, how does the expression turn the x into a 10? What are the things that happen that makes x become a 10? So let's read what happens. If we start off with x first, we multiply by 2 because the order of operation says that multiplication goes before addition unless there are parentheses. And then second, we subtract 8. And then we'll end up with 10. That's how this expression turns an x into a 10. It multiplies the x by 2, then subtracts 8, and we end up with 10. To solve the equation, we want to perform inverse operations in reverse order. We want to turn the 10 back into an x to figure out where it came from. So first, we're going to undo the -8 with a +8. That's the inverse operation. And then second, because we're going in reverse order, we'll divide by 2. So we'll take the 10 and we add 8, and that's 18. And then take the 18 and divide by 2, and that's 9. And then we can check by running 2 through the expression. 2 times 9 is 18. 18 minus 8 is 10. So it works. This is the great thing about equations. We always know if we're right or wrong, so we can check. 2 times 9 minus 8. 2 times 9 is 18. 18 minus 8 is 10. Everything checks out. With equations, you don't need the answer in the back of the book. You can check if your answer is right or wrong. But then again, that exposes why we really want the answer in the back of the book, so we can just write that down instead of actually do the problem and check our work. Students be like, I want the answers in the back so I can check my work. But really, they want the answers in the back so they could write that down and not do the work. You know what I mean? And then students were like, oh, well, the book doesn't show the steps that I need to write down. And then some students are like, oh, yeah, but Wolfram Alpha does. And you're like, oh, sweet. I don't need you anymore, book. So we just need to learn what the inverse operations are. Let's suppose that we add some more operations. We're just going to do inverse operations in reverse order. So let's suppose that I had more space on my page, which I don't. So let's suppose that I have an equation that says 2x cubed minus 8 is equal to 10. Once again, let's figure out what this expression does to turn an x into a 10. So if we start off with an x, the first thing that happens is x gets cubed. So I'm going to say to the third power, because this is our shorthand for what's going on. Second, after we do a third power, because exponents go before multiplication unless parentheses, and multiplication goes before addition unless parentheses, no parentheses. So the next thing is we multiply by 2. And then the third thing is we subtract 8. So here's how this expression turns x into a 10. It raises x to the third power, multiplies by 2, and subtracts 8. So then we'll do inverse operations in reverse order to turn the 10 back into an x. The inverse of subtracting of 8 is add 8. The inverse of multiplying by 2 is dividing by 2. And the inverse of raising to the third power is a cube root or a 1/3 power. Make sure we get the parentheses on the 1/3. So cube root is convenient to write in this form, but more convenient for our calculator, which is what we're going to need, is a 1/3 power. So these are the three things that we're going to do to the 10. We're going to take the 10. 10 plus 8 is 18. Take the 18, divide that by 2, and come up with 9. And then we'll take 9 and raise it to the 1/3 power to find our solution. Now 9 to the 1/3, we're going to have to use a calculator for that. So 9 to the 1/3, 2.08. I'm going to write 2.080 because I usually say round to the nearest 1,000. And just, since this is an equation, we can just check what our answer is going to be. So we can check. I'll take 2 times 2.080 to the third power minus 8. 2.080 to the third power is 9. 9 times 2 is 18. 18 minus 8 is 10. Everything checks out. Notice that it didn't, times 2 and then minus 8. Notice that it didn't come out to exactly 10, but I didn't exactly plug in the cube root of 9. Because I rounded off my 2.0808, sorry, 2.0800838823, because I rounded that off to the 2.08s, I dropped off a bunch of these digits. That's why I didn't land at 10. The more digits I start with, the closer I will end up being to 10. So if I had a different rounded answer, 2.0800, let's say 2.0801, if I raise that to the third power, closer to 9, and multiply by 2, and it's closer to 18, and subtract 8, and I'm even closer to 10. The more digits I keep, the closer we'll be to 10. So we just have to understand that we're not going to get it exactly if we start using rounded off information. So if I take 2 points, actually, let me remind myself. If I take 2.08008 and raise that to the third power, even closer to 9, and then multiply by 2 and subtract 8. We are even closer to 10 that we wanted. Notice that when I used 2.0801, I had 10.000. That's how close it was. I had 3 places. And then in 2.08008, I have now 4 places. More places to start with, closer we're going to be. So now I have 5 places. So just be aware that when we start going for the strange roots that are going to be irrational, we're going to need a calculator to get cube roots of non-perfect cubes or square roots of non-perfect squares and so on. Any questions? This part right here, here we are reading the expression. And here is our plan to do inverse operations in reverse order. So notice that this fits with the model of do the same thing to both sides. So this is still the same thing to both sides. The inverse operations in reverse order are the things that you do to both sides. So for those of you coming from the do the same thing to both sides camp, these are the things we do to both sides. So for those of you coming from the strategy of do the same thing to both sides of the equation, these are the things that we're going to be doing to both sides of the equation. So if I start off with 2x cubed minus 8 equals 10, the first thing that we do to both sides is add 8. And then 2x cubed is equal to 18. And then the next thing we do to both sides is divide by 2. And so x cubed is equal to 9. And then the next thing we do to both sides is raise both sides to the 1/3 power. The reason that I want you to start by reading the expression is I want to make sure you do the same thing to both sides, but you do it in the proper order. Because especially important if it involves exponents and addition and subtraction, because exponents do not distribute over addition. So the reason that we want to read the expression is to make sure that we get the order correct. We read the expression. We read the expression to make sure we get the order correct. The reason that we have to make sure we get the order correct is that some things we can't just switch around. Exponents do not distribute over addition. That's the reason that we have to make sure that we read the expression to get the order correct. Exponents do not distribute over addition. If we go back to our equation, so if we go back as an example, if we go back to the equation 2x minus 8 is equal to 10, this equation involves multiplication and addition, but multiplication distributes over addition. We know we have to divide by 2 and then we have to add the 8, but we can do it in the other order. We can divide by 2 first as long as we divide everything by 2, because multiplication distributes over addition. But now instead of adding 8, we add 4, and we still come up with 9. The reason that we can do this is that multiplication distributes over addition. I was able to divide everything by 2. I was able to divide all the terms by 2. That's why I got to do this. This is not the standard approach to doing this linear equation. You were probably programmed with do the addition first, then do the divide, then divide by the coefficient. First subtract b, then divide by m. But we can divide by m, but instead of subtracting b, we subtract b divided by m, like we did here. But we only can do that. We can change the order. We can undo the multiplication, then undo the subtraction, because multiplication distributes over addition. So the order was okay here because multiplication distributes over addition. That's why we were able to do this order. The same is not true in the equation that we had with 2x cubed minus 8. I can't do the cube root first because I can't take the cube root of a sum and just have it be the sum of the cube roots. That's why I think it's important that we learn to read the expression. Any questions? So this is the game that we want to play. I want to be able to write down an expression involving some operations. For the time being, it'll just be multiplication, subtraction, and exponents. But if I have an expression that says, say, 2x minus 8 cubed equals 10, this expression uses the same 3 operations, a third power, multiplication by 2, and subtracting 8, to turn an x into a 10, but it does it in a different order. To turn an x into a 10 in this expression, first we multiply by 2, then we subtract 8, and now that we've taken care of those two things, third, we raise to the third power. Exponents before multiplication unless parentheses. Exponents before addition unless parentheses. So the parentheses said this is the order. So to undo it, to turn a 10 back into an x, first we'll do a 1/3 power or a cube root. Second, we'll add 8, and third, we will divide by 2. So this is our plan for solving. These are the things that we're going to do to turn a 10 back into the x that we're looking for. So we're going to grab the calculator that I, for some reason, keep putting away. And I'm going to start off with a 10. And first, I'm going to raise to the 1/3 power. Next, I'm going to add 8. And finally, I'll divide by 2, 5.077. This all took place on the calculating machine because the exercise is less about solving equations. It's not about what steps you are performing so that you can solve the equations when you encounter one in your future career as a fill in the blank. It's not even about solving the equation quickly. I don't really care about how long it takes. Undoing the operations that happen to the x. We turn the x, the expression turns an x into a 10. That's what this equation says is happening. Take x, do some stuff to it, and end up at 10. To get back to the x, start off with 10 and undo those things. If we were writing things down on paper, I won't even write something like show your calculations. I just want you to be able to come up with the answer. That's what I want. I want this to take place on your calculator. And I want you to make sure that you perform the correct operations in the correct order. Then once we get the hang of reading the expressions and we've reinforced it by undoing these things, then we can start to be more sophisticated and write down inverses. Write down the function inverse. But for now, this is what we want to be able to do. And we don't want to have to write all this stuff down because look how messy it is. I would have to take 10. I've been doing it in blue. So I'd have to take 10 and raise that to the 1/3 power. Then I have to write down 2.154. Then I have to take the 2.154 and then add 8 to it. That's 10.154. And then take 10.154 and divide it by 2 and come up with a 5.077. That's just too much writing. Especially because all that's, you're just reporting what happened on the calculating machine. You know what I mean? It's not about solving the equation. It's about reading the expression and understanding how inverses work. The reason that I care about this is that later on, we're going to add more different kinds of operations, different kinds of functions. And we're going to have to understand about those different inverses. But this is the core principle. Any questions? Comments? Snide remarks? All right. So there's going to be a new module showing up on the old Canvas, and it's going to be solving equations, and this is where it begins. I want you to perform inverse operations in reverse order. It's not a new thing for those who've been through an algebra class. I'm not doing something new and fancy. It's old stuff, but we're thinking about it in a different way. Still have the same goal. Oh, I forgot. We can still check our answers. I forgot to check my solutions. I just take the 5.077. I know that this has been rounded off, so I'm not going to get exactly 10 because it's been rounded off, but let's perform these operations. We're going to multiply by 2, and then we're going to subtract 8, and then we'll raise to the 3rd power, and we end up back at 10, or close to 10. More digits. More digits through the same function will get us even closer to 10. All right, that's the first thing. It's so some of the old stuff. Reading expressions so that we can write down inverse operations in reverse order.
All right, we are going to practice this some more tomorrow. That's going to do it for today. Everybody have a nice day, and thanks for playing.